พร้อมนะครับ So good afternoon my friend. We are getting back with the mathematical method for physics, and I have many interesting materials to show you today, and I hope you have fun with the classes in the past. So we have 4 students in this class today. I thank you for being with me today. Okay, so let's get back to the material from the previous class just to review what I have talked about previously. So I talked about integration and differentiation, and I told you various methods of computing integrations. So we have trapezoidal rule, we have Simpson's rules, and quadrature. And I also gave you homework problems of trying to compute the quadrature and Simpson's rule for these, for these example. Where's the example? Where is it? Perspective. Okay, this one. Okay, and so I was delighted to hear the news from Patrada that I made a very bad mistake in my lecture last week. If you remember, I tried to show you how you can do integration using Excel, and I have a bunch of these points, and I put the notes in there. But in the previous class, I forgot to put the line number 7 in the Excel file. So I forgot to put that in here last week. And now I put it back in there, and the error gets a lot smaller. Let me erase this line just to simulate what happened last week. If I erase this line here, because I forgot, the error is big, 0.05. If I put it back in like it's supposed to be, now the error becomes 0.0042, much better. So I made a very bad mistake. I'm sorry about that, but hopefully you caught the error and fixed the problem for me. So I made a mistake, and you have to be better than your teacher. Okay, that's the improvement of the generation. So let's get back to the topic for today. Today we are going to continue what I left off from the previous week. I did not talk about finite difference, so I am going to begin the lecture with numeric differentiation. Okay. And before I do that, I need to have a sip of coffee, like this. It's such a happy moment. Okay, so let's see if I seem to have forgotten if am I getting old? I forgot if I hit recording did I do that? Have I?
It's record. Yes, it's recording.
Okay. Damn it. Okay. I think I'm getting old. So we are going to change the subject from integration to differentiation, but not a simple and typical differentiation, but numeric differentiation. That means we are going to do it with computers. Okay. So for example, we have a bunch of data points, not the whole line. We only have this group of data points, x0, 1, and 2, and so forth. I want to know what will be the first derivative of this function at this point, x1, with the circle. So that is the question that we are interested in. So what do? First, we think of the meaning of derivative. Derivative means the change of something. In this case, it is the rate of change. It's the change of the function per the change of the x value. That's what the rate means. The change of f divided by the change of the x of the variable x here. So that's the meaning of derivative. So with that understanding of the meaning of derivative, we can simply just compute the derivative by using this method. So we have 2 points. X2 is the point forward, and x1 is the point we want to know the derivative. So how do we do that? We use this very simple formula. That is the change of the f, in this case f2 minus f1, divided by the change of the x value, like so. And we call this method forward difference. Okay. Now there are other ways to do that. For example, I can use instead the backward point. Again, the point x1 is the point I want to know the information. But I also know the point on the left of x1, which is x0. So what do? I just take this f1 at this point minus the previous point and divided by the difference of the x. And we call this method backward difference. So just different ways to do the same thing. Now you are going to get different number, different prediction for these two methods. Now there are other ways to do that. Any idea? How else can I compute the derivative if I don't use forward point, if I don't use backward point? What else can I do so I can compute the rate of change at x1? Any suggestion? Any idea? Is there other are there other points I can use? I can give you a hint a little bit. If you look at the curve, this curve here, and your eyes is telling you that the slope of the function at f1 is 0. ถ้าคุณมองด้วยตาเปล่าคุณจะกะด้วยสายตาว่าความชันของฟังก์ชันณจุด f1 เนี่ยมีค่าเป็น0ประมาณนี้ And so if the slope is 0, then the forward difference method is not going to be accurate. ตรงนี้มันก็จะไม่ค่อยแม่นยำเพราะว่าค่า2อันนี้มันต่างกันเห็นไหมครับเวลาคุณจับมาลบกันมันคงจะไม่ใกล้0เพราะมันต่างกันอยู่พอสมควร For this backward difference, the change is not going to be 0 because f1 is different from f0 here. So you're going to get a lot of error for this backward difference. Can you suggest other ways of computing the change? Instead of using the forward or the backward, what else can we do? Let's get back to it. Okay. Oh, welcome back from Japan, Tosapon. Okay. All right. Any other ideas? This is a very thing about that you're thinking about these problems and you're doing research on how to get a very accurate differentiation. Again, the change, you can choose 2 points. You can choose the forward point, in which case it's going to be the chain between this point on the right and the middle point. You can choose the backward point. In this case, the chain is going to be this one minus the one on the left. What else? What else can be used to compute the change so that you get yes,
the difference between like x0 and x2?
okay, so the point on the right and the point on the left. Okay, very good. Who was that? I didn't get. Okay, thank you. So that's exactly what I am going to talk about there. So what we call that method is what we call central difference method. So you have this F2 minus F0, the point on the right and the point on the left. Again, you need to divide that by the change of the x value over there. Now, if you just look at that using just your eyes, you can kind of see that this method is going to be very accurate for this example of the graph, because F2 and F0 is very close to each other. If you subtract them, you're going to get, and that will be very good approximation to this F prime. Okay. Now there is, if you look at the textbook and all the books in numerical differentiation, you can find a proof of the error characteristics of these 3 methods. And it turns out, which I'm not going to prove in this lecture, that you have these here. For the forward and the backward, the error is not so good. It is O with the H. But for the central is much better. It is H squared. H squared means that if you reduce the H by a factor of 5, the error is going to be reduced by a factor of 5 squared, which is 25, for example. So central difference is much more accurate than the forward nor the backward. Okay, but in the limit of H going to 0, they will be the same. Okay, because that is the ideal case of the differentiation. Okay, so if you look online or in any textbook, there will be so many recipes for computing this derivative. I can give you some example here of what I found in a textbook or in Wikipedia and so forth. For example, if I want to compute the f prime, the first derivative, I can get that central difference. The point on the right, which is this one, x plus h, and the point on the left, x minus h, divided by 2h, because the distance from here to there is 2h. That's f prime. For f double prime, that is the second derivative, you can get that formula. The point on the right and the left minus itself, 2 times itself divided by h squared. You also have this very fancy, very fashionable, fancy 5-point stencil. Okay, so we use not only 2 points or 3 points, but 5 points. The point on the right, 2 points, 2 left points, and itself. You get 5-point stencil with this formula, and the error is going to be much better. Okay, h to the fourth power. So there are so many recipes you can do, and what I want to do in this lecture is to give you a more different stories of what you would see normally in a typical math method in physics. เนื่องจากมันมีอยู่หลากหลายสูตรต่างๆที่เราจะได้ไปเรียนกันนะครับเพราะนั้นผมก็จะไม่ไปโฟกัสที่สูตรต่างๆแล้วก็พิสูจน์ว่าเออร์เรอร์มีค่าเป็นยังไงในแต่ละสูตร แต่ผมจะพยายามพาคุณไปมองในอีกมุมมองอื่นๆนะครับที่คุณอาจจะยังไม่เคยเห็นในการสอนนะครับเรื่องของ Math Method for Physics นะครับมองในแง่ของ Perspective มากกว่าในแง่ของรายละเอียดของตัวแต่ละสูตรนะครับ so I'm gonna give you in this hours the perspective of how we use numeric differentiation to understand physics much better. So in science or in physics, you can split what you learn into 3 categories. You can think of it as the initial data of information, okay? And that is the beginning of the learning process. You learn about the data, like these formula here. These are the data. Now, as you learn more about the data, you gain understanding of the things in physics. ความรู้มันก็จะขยายขอบเขตได้กว้างขึ้นมีภาพพจน์เห็นภาพชัดเจนมากขึ้นก็จะกลายเป็นความเข้าใจก็คือ understanding and at the end once you have this huge understanding you get to the wisdom part and so in this lecture I am going to show you how you go from data the recipes to the understanding and at the end the wisdom of physics so let's take this long journey to understand the wisdom of physics and see if I can do this if I can do as I promise you but before that I need to have a sip of coffee so what would be the perspective หรือว่าเป็นมุมมองใหม่ๆที่คุณจะได้เห็นอย่างตื่นเต้นที่เกี่ยวข้องกับการหาค่าดิฟต่างๆหรืออนุพันธ์ต่างๆนะครับ and so let me give you an example if I have a bunch of points there and I can use a central I can use this formula to compute second derivative at this point it is the point on the right plus on the left minus twice of itself minus 2fx the whole thing divided by x squared that is an example now if you look at this in another ways you see that the finite difference is a relationship between this point and a neighborhood so what is a neighborhood neighborhood is the group of points surrounding the point we are talking about neighborhood ก็คือบ้านที่อยู่ข้างๆเคียงนะครับบ้านที่อยู่รอบบ้านของเราถ้าเราอันนี้คือบ้านเราตรงกลางนี้นะครับแล้ว neighborhood ก็คือบ้านที่อยู่ข้างๆนะครับบ้านทางซ้ายทางขวาแล้วก็จุดที่อยู่ทางซ้ายทางขวานะครับ so this is the relationship between ourselves our home and the neighborhood okay so this is the picture of our neighborhood we have this point the fx and that is fx plus h that is fx minus h so this formula here tells you the relationship between this guy our home and the rest of the homes surrounding here so what is that relationship this here we look at this on the left this point second derivative and we can compute that using the neighborhood's value I can get that information from using these values multiplied by 1 coefficient minus 2 and plus 1 I get back the data that I want over here okay so that is what we mean by finite difference relationship between this point and other homes surrounding us okay so we are going to move forward to something that we call differential equation you've seen this all the time in physics class let me give you an example we have here is a Laplace equation you've seen this in I don't know maybe you know that let's ask one of my students have you are you taking any other class besides math method this semester
classical dynamic
classical mechanic, talking about the motion of the objects in the skies and the heaven. What else? So that's mechanic. Anything else? Quantum mechanics. Okay. Are you taking this electromagnetic courses in this semester?
No, for me it's
No?
next semester.
Okay, very good. So you have not seen this Laplace equation yet then. Okay, let's talk about that example in this lecture. So we can that's what we call Laplace equation. F second derivative is equal to 0. Now, this what we call DE or differential equation is also a relationship between points in the neighborhood. Now, you might not understand what I mean by that at this slide, but I promise you that by the end of this hour, you will know what I'm talking about. But just keep with me for a moment. So DE is a relationship between points in the neighborhood. Okay, and every DE has a story. So when you see this equation or any equation that you see in physics class or in your research, always think about a story that equation is telling you. So to understand what I mean by this slide, it may seem difficult at first now, but let's look at an example. A story of Laplace equation. Okay. Now, Laplace equation, when you see this equation in a textbook or online Wikipedia, it's written in this form. On the left, you have this triangle and the square. Now, what this means is that in one dimension, on the left is simply second order derivative of x is equal to 0. That's in one dimension. What about two dimension? You have an additional term of the y direction, y-axis. So we have this d square, dy square added to the 2D for 2D. What about 3D? You have three terms like so. So very simple way of shorthand writing of these here into this very simple symbol in this way. So let me give you an example. Okay. Now, if you study electrostatic, okay, in physics, we see this very often. It is about charges and it's also static. It's not moving in time, electrostatic. We have an object like this, and we have charges on the surface of an object. Maybe this point charge here and there and so forth. Now, we can think about this big picture into two regions. The region on the surface of the object. In this region, you have charges around the object, and the Laplace of the F is not going to be 0. What is F? F is the potential in volt, okay, of a system. What about the region where you have no charges or in space? In this case, it can be proved with mathematics, or maybe it's not a proof, it's a theory, that the Laplacian of the F of potential is always 0 in this case. So this is the example of the Laplace equation. The Laplacian of F is always equal to 0 for electric potential, okay, outside of the charge region. So that's the introduction of the Laplace equation. Now, that's math, okay? It's all mathematics. What does it mean in physics? When I say something like this, when I say that second order derivative of f and so forth, it's just the mathematics. What does it mean in physics when we do something like this? Okay, so let's find out what it means. In one dimension, we have this Laplace equation like so. On the left is a second derivative of f. On the right, it's just 0. Now I can use what we learned before, what we call finite difference, like this, and I can substitute this to the left-hand side of the equation. But just to show you what I mean by the neighborhood, let's say I have a bunch of homes. This is my home here in the middle. The middle point is my home. And this is my neighbor home, one on the right and the ones on the left with this label of x plus h and x minus h, okay? So I can substitute this formula using finite difference back into the left-hand side of this equation. I get that here. Now, the h square is gone. Why is that? I mean, in the beginning of the formula, I always have h square. But when I put it back in here, the h square is gone. Does anybody see why? Let's go slow a little bit. Yes, so I still have this formula. My neighbor add to the left, neighbor add to the right and left, and minus twice myself. But I don't have this dividing h square in this equation. Seems to disappear. Why is that? Does anybody see why?
Because
So,
u equal to 0 and h square is moved and multiplied with 0.
Very good. So we can say that we can multiply h square on both sides. When you do that, on the right you still get 0. On the left, they will cancel the dividing h square there. Okay, very good. So with that beginning expression, I can rearrange the term a little bit, and I get that pattern, which is my home, myself, is my neighbor on the right, on the left, divided by 2. That's a very curious pattern. Divided by 2, what does it mean? It means our home or my home is an average of the surrounding, okay? Only for this example of one dimension, okay? It may not be true for two-dimension Laplace equation, but we'll see. But at least in the 1D, I get that relationship coming from Laplace equation. That is, the value of my home is an average of the surrounding, okay? What about 2D? In 2D, we have the two axes. We have x and the y, and both with derivative and 0 on the right-hand side. Now I can apply the same finite difference method. But before that, let me show you the homes of my neighborhood. Here I have this in the middle is my home. Now the f function is then a function of x and y. Not x anymore, but x and y. So I have four neighbors surrounding me. The one and the two on the x-axis, and other two on the y-axis, like this. I can go back to my finite difference method and write down how I compute the second derivative of x. Notice here that when I doing this derivative respect to the x alone, I simply deviate or change my x position only. This is my x plus h and x minus h. So when I do this, I only change my x position. What about the y derivative? The same concept. I just simply change my y derivative. Here we have y plus h and y minus h. It's going to be my neighbor here and there for the y derivative. So I do this, and I want you to do this at home, okay? And you can show by very rigorous mathematics that you get this expression, that the f at my home is simply the whole neighborhood here, 4 of my points divided by 4. That's very curious. Dividing by 4 is the same thing as saying that our home is then again an average of the surrounding. Now you can do this for 3D, and it will be true for 3D. And for 3D, you will have divided by what number? What do you think? In 3D, you have this x-axis, which you're going to have this number 2 coefficient from the x-axis. You have another y-axis, you have another number 2 coefficient. You have the z-axis, and you have another 2 coefficients. So what do you get? What is the dividing number for 3D?
6.
Number 6, very good. So we have then again the same conclusion of the understanding of what Laplacian operator means, of what Laplace equation means in this case, that our home, the value of that function must be the average of the surrounding. That is the condition of the Laplace equation, okay? So we continue with the story of Laplace equation here. In the beginning, we have this physics, and from physics, we know that we can build this mathematics, that the Laplacian of the f must be 0, must be 0. Now, that's the data. That's the data. Because we only know how to do that in mathematics. That's only the data. Now, once we get to the understanding of what really means, it means that the potential of the function is an average of the surrounding point. That is the understanding. Okay, and at this, happy to understand more about what this Laplacian operator is telling you. It tells you that the average, the value of that point is always the average of the surrounding points. Now, what about the wisdom? What about the wisdom? Seems to be somewhat difficult to get. You know, seem to be I don't know, difficult to understand the wisdom. Anyway, if so far I have gone too fast, let me know, okay? If I because I can go much slower. So let's go with the, what does wisdom mean in this case? Can we understand even more than the simple meaning of this Laplace equation? Well, there is. Before we go to the wisdom, in fact, I learned about the wisdoms of this Laplace equation when I was very young. I thought maybe I was just like your age. I think I was about 25 years old. Think about that. 25 years old, I learned about the wisdom of this Laplace equation from Richard Feynman, from his book. This book here I read when I was doing my PhD. And let's go online and get to know who he is a little bit. He is one of my heroes in physics. Let's see, I have this link that I actually translate many of his writing and speech. Let me see if I can oh, I can't. I can go to Google Chrome. Where's my Google Chrome? There you go. Now I can go to my, if you go to my website and click on my writing in Thai. So this is the speech given by Richard Feynman after he got a Nobel Prize in Physics. Dear Chen can read about it in English online in this website, but I translate it into Thai language. You know, it's very inspiring speech. It tells us about how Feynman learned to be a physicist. Okay, and at the end, I also made a video clip that translate into Thai language. Let's look at this. Watch this video together, maybe briefly, only 2 minutes. Okay, it should be quite brief. How do I do that? Okay, there you go.
I have a friend who's an artist, and he's sometimes taking a view, which I don't agree with very well. He'll hold up a flower and say, "Look how beautiful it is." And I'll agree. And he says, "You see, as I, as an artist, can see how beautiful this is. But you, as a scientist, take this all apart, and it becomes a dull thing." And I think that he's kind of nutty. First of all, the beauty that he sees is available to other people and to me too. I believe, although I may not be quite as refined as aesthetically as he is, that I can appreciate the beauty of the flower. At the same time, I see much more about the flower than he sees. I could imagine the cells, the complicated actions inside, which also have a beauty. I mean, it's not just beauty at this dimension of 1 centimeter. There's also beauty at a smaller dimensions. The inner structure, also the processes, the fact that the colors and the flower evolved in order to attract insects to pollinate it is interesting. It means that insects can see the color. It adds a question. Does this aesthetic sense also exist in all forms? Why is it aesthetic? All kinds of interesting questions which the science knowledge only adds to the excitement, the mystery, and the awe of a flower. It only adds. I don't understand how it subtracts.
Okay, very inspiring, Professor Feynman. So you can see beauty, not just what the eyes can see, but also how your mind can understand things. Let's get back to the wisdom of electrostatic. Okay, so what is this wisdom that I found in his lecture in physics? There was this one topic that Feynman discussed in his book. It says that it is impossible to balance a positive charge in an empty space. Now, what does he mean by that? Let me elaborate on the meaning of this quotation. Okay. Suppose we have a system and a universe here, and you know, universe is full of charges. You have many water molecules, and that is charges. You have this negative, and you have this positive. Maybe you have an object which is made of atoms and nuclei and so forth. You have so many charges. So a universe is full of charges. Okay. Now because of these charges in the system, you will have electric potential around the empty space of the universe. Now, suppose you look at this empty space of the universe. There is a point charge there. Okay, that's very tiny and very cute point charge in there. Now, this theorem that Feynman is talking about, it says that the charge cannot be in equilibrium. If you only have electrostatic forces, force alone over here. So what does it mean? Okay, let's go to the next slide. Maybe if you don't get this slide totally, it's fine. Okay, and wait until the next slide. You will see more what it means. So we have this universe, a system with charges, and these charges will produce electric potential, like so. This vroom, 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 surrounding the region in the environment. You have this potential coming out. Okay. Now, this potential, of course, obeys a laws of physics, obeys the Laplace equation. That equation is Laplace of f is equal to 0. That's what Laplacian equation means. That's f. Now, you have this charge q in this empty space, okay? And also, if you think about this system in terms of potential energy, you can compute energy of a system in this orange region using that formula. Is the charge multiplied by the potential of the system. So my u is that function. Okay. Now let's get back to what we mean by stable equilibrium. It means that, say, if we have a ball, let's talk about mechanic equilibrium. ในเชิงกลศาสตร์ครับ we have a bowl there and we put an object at the bottom of the bowl. Now this is what we call equilibrium, because if you, let's see, like if I can see my my camera, I need to see my camera. Okay, yeah. Suppose I have a bowl there and that my fist is my object. Equilibrium in that is stable means if I move the object a little bit to the right, it always come back to the bottom of the bowl. If it moves to the left, it comes back. Okay, so it always comes back to the starting point. That's what stable equilibrium means in physics. Now, in terms of the mathematics, it means that the potential energy always at the minimum. Like in this picture, this is my energy for gravitation. Is mg times the height, mgy, that's my y. So at the bottom of the bowl, my energy is minimum. So that's the condition for having a stable equilibrium. For mechanics, now let's get back to electric system. Okay, so this is my formula for the energy of the electric system. Well, let's use the home and the neighborhood analogy. This is my home. The point I am talking about maybe is right here, right there. Okay, this is the point, my home, and these are my neighbor on the right and on the left. Okay, now if I want to solve this equation to get the f function, to get the potential at any point, I need to solve Laplace equation. If I do that solving Laplace equation, what do I get? Suppose I know that at my neighbor on the left, potential is 1 volt. What about the one on the right? He's got 5 volts. What must be my potential? What do you think? What do you think? According to what we have discussed so far, that my home is always the average if I is to satisfy the Laplace equation of my neighbor. On the left we have 1 volt, and on the right we have 5 volts. What would be the potential at this point? Anyone? Let's pause. The what?
3.
Very good, 3, because 3 is the average of 5 and 1. If you add 1 to 5, you get 6. Divided by 2, you get 3. So very good, 3 is the average. So because we want the function f to satisfy Laplace equation, you must have that kind of voltage at the points. Now, let's say we have a minimum. What does it mean, minimum? For example, my home has 3 volts, and my neighbor is 5 on the left and 5 on the right. So I'm having a minimum here, and that is not possible because we are violating Laplace equation. See, Laplace equation tells us that the point has to be the average of the neighborhood, and this point cannot be the average. And that means that you can never have a minima in Laplace equation system. What does it mean? It means there is no stable equilibrium due to this force alone. Okay, you can never have equilibrium because of the Laplace equation. Now that's some kind of understanding. It has a lot to do with mathematics and so forth. Let's go to the wisdom of the topic over here. Okay. Now, what is the wisdom of it all? If you look at the universe is a big place. Now, the fact that I am talking about at this moment, it means that my body, an object, and my home is a stable equilibrium because we don't just explode. We can be stable for a while. And that means that for the universe to be stable, we need to have more forces. Okay, we need to have more forces in the universe. We cannot just have one electric force alone. That would not be enough for the universe to sustain itself. Okay, and that is the wisdom, and that wisdom comes from a very advanced interpretation of the mathematics and physics. We learn about how we understand the Laplacian operator, and then we combine that with the understanding of the equilibrium, and we get that here. So we need to have some other interaction for universe to be stable. For me to exist, I need to have quantum mechanics interaction. I need to have gravity. I need to have some other things, nuclear charge and nuclear forces and so forth. Okay, that's, I think, is very amazing conclusion from just simple Laplace equation there over there. Think about how we have gone so far in the understanding. In the beginning, we only know that that symbol means that mathematic operator, and then we understand the sort of meaning of this mathematics, that it is an average of the surrounding, and we move even further to understand the universe and how the universe needs to have more forces to be stable. Okay, and that is the end of the story of Laplace equation. Like I said, every equation has a story. Okay, now, is there any question before I move on to the next loving story of a differential equation? Anything? Any comments about the wisdoms, about the how we interpret คอมเมนต์เกี่ยวกับการตีความตัว Laplace operator ว่าแปลว่าอะไรนะครับที่มันเป็นศูนย์ตรงนี้เท่าที่อธิบายมานี่ไม่รู้ว่ามันเคลียร์ไม่เอ่ยก็ผมเพิ่งลองอธิบายให้คุณฟังเป็นครั้งแรกนะครับอันนี้ยังไม่ได้attempt ที่จะไปเล่าให้รุ่นอื่นๆฟังน่าจะพอเข้าใจอยู่เนาะ
เข้าใจค่ะ
ไทยซับหน้านี้ให้หนูหน่อยค่ะ
ไอ้นะครับ
ไทยซับหน้า Universe ให้หนูหน่อยค่ะ
โอเคไทยซับ
ไทยซับ
โอเคเดี๋ยวนะครับก็ถ้าเราจะมีดนตรีนะครับเมื่อก่อนนั้นนะครับผมก็ได้เริ่มอ่านข้อความที่เป็นwisdom เป็นครั้งแรกที่ได้เจอก็อยู่ในตำราของไฟแมนนะครับเล่มที่2นะครับซึ่งเราได้เรียนรู้มาในสไลด์ผ่านๆมาแล้วว่าเวลาที่เราเห็นตัว Laplace Equation นั้นนะครับมันหมายความว่าจุดนั้นเนี่ยต้องเป็นค่าเฉลี่ยของเพื่อนบ้านของเรานะครับต้องเป็นค่าเฉลี่ยเพราะฉะนั้นถ้าเราเอาตรงนี้มาผนวกกับความเข้าใจเรื่องของstable equilibrium มันก็จะกลายเป็นความเข้าใจที่เป็น wisdom ขึ้นมาสูงขึ้นนะครับที่จะ unlock ความลับของจักรวาลนะครับว่าจักรวาลเนี่ยทำไมมันถึงมีแรงต่างๆอยู่หลากหลายมากเหลือเกินทำไมต้องมีแรงเดียวไม่ได้นะครับแรงที่ของอยู่ในจักรวาลเนี่ยส่วนใหญ่บนโลกมนุษย์เนี่ยมาจากประจุนะครับเพราะว่าสสารเนี่ยมันจะมาจากอิเล็กตรอนประจุลบมาจากนิวเคลียร์ประจุบวกนะครับแล้วมันก็จะมีแรงพันธะต่างๆกันเพราะนั้นส่วนมากเป็นประจุแต่อันเดียวไม่พอนะครับมันทำให้ระบบมันไม่เสถียรต้องมีอย่างอื่นด้วยนะครับและอันนี้ก็คือเป็นวิสตอมที่เราได้มาจากการวิเคราะห์นะครับในครั้งนี้นะครับมันจึงต้องมีอันตรกิริยาทางควอนตัมมันต้องมีเรื่องของโน้มถ่วงเข้ามาเกี่ยวข้องต้องมีนิวเคลียร์มาเกี่ยวข้องจักรวาลถึงจะสามารถอยู่เป็นรูปเป็นร่างที่มันคงตัวขึ้นมาได้นะครับไม่งั้นมันจะไม่เสถียรนะครับมันจะต้องสลายไปนะครับตามสมการทางคณิตศาสตร์นะครับโอเคทีนี้อะไรวะเนี่ยเปลี่ยนหมวดเป็นภาษาอังกฤษนะครับ so like I said every equation has its story now Dichen told me last week that she wanted me to talk about diffusion equation somehow was that right did you request DE
yes I just
very good so I prepare this story this loving story about diffusion equation for the class just for you and the rest of the students here so let's talk about diffusion process in here I have liquid water in a container and if I put color pigments or dye there on the left I drop color pigments there the pigments spread out it's spread out and we call this diffusion process หรือการแพร่นะครับการแพร่ของสีของแก๊สหรือว่าของแก๊สก็เช่นเวลาที่คุณปล่อยปุ๋งก็จะมีแก๊สไข่เน่านะครับแล้วการแพร่เนี่ยมันก็จะไม่ต่างอะไรกับที่คุณเห็นในภาพเนี่ยแก๊สไข่เน่าเนี่ยมันก็จะค่อยๆกระจายขยายพื้นที่ขึ้นจากบริเวณที่มันอยู่ใกล้ๆก้นคุณแล้วมันก็จะขยายออกไปโดยรวมเข้าอยู่เต็มพื้นที่ของห้องนะครับ so the process that happens in diffusion is that the concentration of the particles of the color pigments spread out it's spread out and eventually you get this equilibrium that every point has the same concentration okay that's the end game of diffusion process okay equilibrium now if you look at an equation it looks like this you have this on the left hand side you have this Laplace but look on the right is no longer zero but something else it has a constant and this change of f per time but by the way f is the concentration of the color pigment so that's the mathematics on the left hand side you have this Laplace of the f on the right hand side you have this constant we call this diffusion constant times the change of the f over time okay so that's mathematics what does it mean in physics okay let's get to the understanding of the physics equation behind diffusion okay now if I focus my attention to the diffusion process in this container here I can look at two different regions ลองดูใน2พื้นที่ลองดูแล้วก็ so we want to understand what this means this Laplace of f okay with the right hand side is not zero what does it mean now again I can go back to my neighborhood analogy I look at this here this is my home and this is my neighborhood. It's on the right and on the left. I can apply the same technique that I use, find a different technique, and I can show this, and you can do this at home, but you can always show the following here, that this Laplace of f, it measures how much below the average our home is. Okay, let me give you an example. Let's say if I compute this Laplace of f and I get this +5 value. What does it mean? It means that our home is much below the average. It means that the average is very high, and I'm here very small value compared to the neighbors, +5. It tells you how much below the average our home is. What about if I compute the Laplace and I get -5? What does it mean? It means the opposite. It means that you have more than neighbors. You have a lot more than neighbors. What about in the middle? Suppose I compute my Laplace of f and I get exactly 0. What does it mean? It means that you have the same as neighbor on average. And that's the Laplace equation. Okay, so Laplace equation is when you have the 0 on the right-hand side only. But with diffusion, it's not always 0. It can be positive, it can be negative, but what this means is the following here. It tells you how much below the average the function f is compared to the neighborhood. Okay, that's the meaning. And you can show that by using a simple technique of finite difference. So let's go to the interpretation of the diffusion equation. So focus on the two regions of the liquid. Maybe at this point first and the second point here. So in this region here, you don't have many pigments. Okay, you have very low concentration here, not so many pigments here. So that means, what does it mean? It means that we have below average of the pigment color at this region. Let's say, for example, I compute this, I get +5, +5 below the average. What about this region down here? And down here we have this color pigment very high above the average value. Let's say, I seem to go step ahead. Okay, let me get back. Let me step back forward one step. Okay, and here we have the pigment below the average and a positive value. If I look at the right-hand side of this equation here, okay, we have df dt. It means that this df dt is positive because we have plus number here. When f is positive, what does it mean? It means that the pigment is pouring in. Okay, the pigment is increasing because df dt is positive. Okay, that's what's happening here in this region. Okay, what about this region? If concentration is more than the neighborhood, let's say I get this -5 value, and I compare this -5 to df dt. What does it mean? It means that in this case, the color pigment are leaving the region. It's going away. You see, if I summarize this thing, this is what you get. It means that if you have less than the neighbors, then in the future you get more from the system. You see, that's what diffusion means. If you have like this here, in this region you have less than the neighbor, you are gaining more pigments. Okay, if you have less than the neighbor, you always get more from the system. In the future means you have this derivative. It means in the future, in the next time step, you always get more if you have less than a neighbor. On the other hand, if you have more, you are giving away to the neighborhood. And that's why at the end, you go to the end game of the equilibrium, that everyone has the same value of the concentration. Okay, so that's the meaning of the diffusion equation in the understanding. I would say if you do this, if you follow this logic and understand it, I would say you have reached the level of professional physicist. Now you can always go back and try to watch the video for the second time and see what happens. Let's ask Miss D Chen. This is D Chen.
Yes, I just.
So are you happy with the explanation of the meaning of the diffusion equation?
Very much.
Okay, very good. So that's the basic concept of why we built this equation. On the left, it tells you how much below the average is. On the right, it tells you how much you are gaining more and more. If you are below the average, you will gain more, and that's why the whole neighborhood always get back at the end the same value across the region. Okay, and D here is tells you how fast the system evolved in time. Okay, now that's the concept. Now the concept will not be as useful if you don't do homework problems or you don't do the actual calculation. So I then prepare for you this next section of the lecture of how you actually solve an equation, okay, using a program. Well, an example will be in one dimension. Okay, so we have a few. Let's see. Should I take a break? That will be. It has been only an hour, really, of the lecture. Okay, but I'm guessing maybe you are tired because of all of this concept. And also, I don't even have time to finish my coffee. Before I show you how to actually solve and implement the in the program, let's take a break for 10 minutes, and then we'll be back briefly. Okay. Let's see. Break. We'll be back at 14. Now it's 14:09, 14:20. Very good. Okay, it's coffee break. Okay, and I'll put my music on. I mean, I'm still here, but maybe I'll go to the restroom. I just want to take exercises before I practice my kung fu in programming. And I hope you are. Yes.
แต่ยังไม่ไปไหนใช่ไหมคะ
ไม่ได้ไปไหนยังนั่งเล่นคุยกันสับเอ
งั้นเล่าหน้าเมื่อกี้ให้ฟังอีกหน่อยนะ
เล่าเรื่องอะไรครับ
หน้าม่วงๆเมื่อกี้ค่ะหนูแปลออกได้ครึ่งต่อครึ่งเราไม่เข้าใจอ่ะ
หน้านี้
หน้าย้อนกลับอีกนิดนึงค่ะ
โอเคเดี๋ยวนะครับ
ใช่เลย10-30ค่ะ
โอเค
อือฮึ
หน้านี้ก็คือเรากำลังพยายามที่จะแกะสมการ diffusion ว่ามันแปลว่าอะไรนะครับถ้าถอยไปหน้าหนึ่งผมก็กำลังจะพยายามอธิบายว่าผมอยากจะพยายามตีความโดยใช้คณิตศาสตร์แล้วก็ให้คณิตศาสตร์สร้างเป็นความเข้าใจว่าไอ้ Laplace ของฟังก์ชัน f มันแปลว่าอะไรเมื่อก่อนเราเคยเรียนสมการ Laplace ที่ด้านขวามือสมการเป็นศูนย์เสมอซึ่งถ้าเป็นอย่างนั้นเนี่ยมันก็แปลว่าบ้านเราเป็นค่าเฉลี่ยของเพื่อนบ้านใช่ไหมครับแต่ถ้ามันเป็นค่าที่ไม่เป็นศูนย์เนี่ยมันจะแปลว่าอะไรนะครับผมก็เลยลองทำกันบ้านดูแล้วก็เอาไปแกะเป็นสมการแล้วก็ใช้มุกเก่าๆเดิมๆนะครับก็พิสูจน์ได้ว่านะครับไอตัว Laplace ของ f เนี่ยมันแปลว่ามันเป็นค่าที่บ่งชี้ว่าบ้านเราเนี่ยมันต่ำกว่าเฉลี่ยอยู่เท่าไหร่นั่นเองต่ำกว่าเท่าไหร่นะครับยกตัวอย่างเช่นถ้าเกิดมันได้บวก5สมมติว่าคุณไปคำนวณฟังก์ชันแล้วมันได้เลขบวก5มาเนี่ยอันนี้แปลว่าค่าของบ้านเราเนี่ยมันต่ำกว่าค่าเฉลี่ยอยู่5หน่วยเทียบกับเนเบอร์นะครับประมาณนี้ถ้าเครื่องหมายมันสลับตรงข้ามไปทางด้านลบมันก็จะแปลตรงข้ามก็คือเรามีมากกว่าเพื่อนบ้านอยู่5หน่วยแบบนี้ถ้าเป็นศูนย์พอดีเป๊ะก็แสดงว่าเรามีค่าโดยเฉลี่ยโดยเฉลี่ยนะเท่ากับเพื่อนบ้านพอดีเป๊ะมันก็จะย้อนกลับมากลายเป็นสมการลาพลาสธรรมดาเหมือนที่เราเคยพูดกันแต่ทีนี้เรามีเงื่อนไขมีกรณีที่มันเป็นทั่วไปมากขึ้นคือมีทั้งบวกก็ได้ลบก็ได้แล้วก็เป็นศูนย์ก็ดีนะครับคีย์เวิร์ดก็คือถ้าเป็นศูนย์ก็คือมันจะกลับไปเป็นอันเก่าที่เราเคยพูดเมื่อสไลด์ก่อนหน้านั้นก็จะกลายเป็นสมการลาพ
ที่
ลา
เป็นอยู่ตร
ส
งกลางค่ะ
ใช่ครับคือเราจะมีค่าเฉลี่ย
ค่ะถ้าเป็นบวก5นี่หมายความว่าบ้านเราจะขยับไปใกล้กับเพื่อนบ้านมากขึ้นอย่างเงี้ยเหรอคะหรือว่าไกลถ้าเป็นลบอย่างนี้ปะ
ลบคำว่าบนโลนี่ก็คือมันไม่ได้พูดถึงเชิงตำแหน่งคำว่าบนโลก็คืออาจจะเป็นเงินเดือนรายได้เรียกว่าค่าสัตว์ไฟฟ้าหรืออะไรก็แล้วแต่ครับเช่นเอาเป็นเงินเดือนก็ได้ถ้าเป็นบวก5หมายความว่าผมได้เงินต่ำกว่าเพื่อนบ้านอยู่5 บาทอะไรประมาณเนี้ยนะคีย์เวิร์ดก็คือ below average ถ้าเป็นลบ5มันก็จะเป็นตรงกันข้ามเห็นนะอันนี้แปลว่า below ก็คืออยู่ต่ำกว่าเพื่อนบ้านมากน้อยแค่ไหนต่ำกว่าค่าเฉลี่ยมากน้อยแค่ไหนโอเคนะที่เราก็เลยมาดูสไลด์หน้านี้นะครับอันนี้คือสมการการแพร่ใช่ไหมครับแล้วก็ลองมาเปรียบเทียบใน2พื้นที่นะครับพื้นที่สีขาวนี่ก็คือจุดตรงนี้มันไม่ค่อยมีสีเท่าไหร่มันยังเป็นจางๆอยู่ส่วนตรงนี้มันยังเป็นเข้มๆก็คือเข้มมากกว่าค่าเฉลี่ยนะครับตรงนี้นะตรงนี้จางค่าเฉลี่ยนะครับลองมาดูทั้ง2พื้นที่กันมาดูพื้นที่แรกนะครับตรงนี้เนี่ยมันจางกว่าค่าเฉลี่ยหรือมัน below average แล้วก็แปลว่าไอ้ตัวลาพลาเซียนเนี่ยมันได้เป็นบวก5นะครับเช่นค่าบวกนี่พอคุณเลือกเอาโยงเอาด้านขวามือสมการมาใส่ที่มันมีพื้นหลังสีเขียวเนี่ยครับพอเป็นบวก5เนี่ยแปลว่าอะไรดิฟเป็นบวก5ดิฟเทียบกับเวลาเป็นบวก5แสดงว่ามันกำลังเพิ่มขึ้นใช่ไหมถูกไหมครับมันกำลังเพิ่มขึ้นแสดงว่าปริมาณเม็ดสีมันกำลังมากขึ้นหรือเขียนเป็นภาษาเป็นทางการได้ว่าเม็ดสีกำลังเทเข้ามาเม็ดสีกำลังเทเข้ามาเห็นไหมถ้าเกิดเม็ดสีอยู่ข้างในเนี่ยมันต่ำกว่าเฉลี่ยมันก็จะมีการเทเข้ามาข้างในมากขึ้นลองไปดูฝั่งตรงข้ามตรงนี้เนี่ยความเข้มของสีมันสูงใช่ไหมครับสูงกว่าค่าเฉลี่ยสูงกว่าเพื่อนบ้านก็คือเป็นติดลบถ้าเกิดเรามาโยงมาใส่ด้านขวามือสมการดิฟเทียบกับเวลาติดลบแปลว่าอะไร
แปลว่าความเข้มลดลง
มันก็กำลังลดลงใช่ไหมครับมันกำลังต่ำลงมันกำลังวิ่งหนีเม็ดสีกำลังวิ่งหนีออกจากพื้นที่ตรงนี้นะครับเห็นไหม ก็แสดงว่าถ้าคุณเอา2เงื่อนไขนี้เอามารวมกันให้กลายเป็นสตอรี่เดียวกันนะครับมันก็จะบอกได้ว่าไอ้ตัวเนี้ยสมการ diffusion เนี่ยมันแปลว่าถ้าเกิดคุณมีน้อยกว่าเพื่อนบ้านเช่นกรณีนี้ในอนาคตคุณก็จะมีมากขึ้นมันก็มาจากระบบคำว่าในอนาคตก็คือ in the future ทำไมต้องว่าในอนาคตเพราะมันเป็นดิฟเทียบกับเวลาคุณดิฟเนี่ยมันจะหมายถึงการเปลี่ยนแปลงไปข้างหน้าใช่ไหมครับไม่ใช่ปัจจุบันอย่างเดียวแต่มีการเปลี่ยนแปลงไปข้างหน้าด้วยนะครับนั่นก็คือความหมายของสมการ diffusion นะครับถ้าคุณมีต่ำกว่าบริเวณรอบๆคุณก็จะมีมากขึ้นในอนาคตจนสุดท้ายแล้ว end game ก็คือทุกคนก็จะได้เหมือนกันหมดเป็นแบบนี้นะ
มีเท่าคนอื่นเขา
ตามครับก็นี่ในสไลด์เดียวเราได้มีความเข้าใจมากขึ้นว่าสมการเนี่ยเมื่อก่อนถ้าเป็นคุณยังเรียนในเบื้องต้นอยู่คุณก็คงจะพอแค่รู้ว่าไอ้เครื่องหมายสามเหลี่ยมกำลังสองมันแปลว่าอะไรเห็นไหมคิดอันดับสองก็ว่าแล้วก็ท่องไปแล้วก็ไปคิดเลขก็ปัดย้ายข้างไปย้ายข้างมาแต่คุณอาจจะไม่มีความเข้าใจหรือไม่มี understanding ว่ามันแปลว่าอะไรกันแน่แล้วตอนนี้คุณเริ่มมีขึ้นมาแล้วนะครับโอเคก็คงจะรู้สึกนึกสมควรว่าอยากได้มากขึ้นอีกครับ
ได้เข้าใจด้วยเป็น
รู้แล้วทำไมคุณถึงเข้าใจตรงนี้นะครับเพราะว่าในอนาคตคุณสามารถจะถ้าคุณทำบ่อยๆคุณทำเก่งคุณจะสามารถที่จะย้อนกลับได้พอคุณเริ่มมีไอเดียอะไรสักอย่างหนึ่งคุณจะสามารถเปลี่ยนไอเดียให้กลายเป็นสมการได้แล้วก็เอาสมการเอาไปใช้แก้โจทย์ต่างๆเหมือนกับพวกเกจิอาจารย์ทางฟิสิกส์ทั้งหลายนะครับเขาตอนแรกเขาจะมีแค่ไอเดียนะครับไอเดียเกี่ยวกับเรื่องของปรากฏการณ์ทางฟิสิกส์แล้วเขาสามารถจะเปลี่ยนไอเดียให้กลายเป็นสมการย้อนกลับมาเป็นสมการแล้วก็ให้สมการไปศึกษาระบบต่างๆก็ดูว่ามันแม่นหรือเปล่าถ้าแม่นก็รู้เราได้สูตรลับของธรรมชาติแล้วว่าเป็นอย่างนั้นอย่างนี้นะครับโอเค
อย่างนี้เราก็ต้องศึกษาแบบว่าหลายๆระบบเหรอคะเพื่อที่จะเทียบเคียงกัน
ถ้าคุณชอบด้านนี้ใช่ไหมล่ะมันก็ถ้าผมชอบฟังเพลงมันดูผมชอบฟังเพลงเก่าๆผมก็ต้องฟังหลายๆเพลงเพราะผมยิ่งฟังยิ่งมีความสุขถูกไหมล่ะก็ขึ้นอยู่กับว่าชอบไหมเผอิญผมชอบด้านนี้ผมก็ทำที่ผมมีความสุขแล้วผมก็สมการนี้ก็มันมีความเข้าใจแล้วผมก็จะไม่พอก็จะหิวอีกอยากจะเรียนรู้สมการอีกนะครับผมก็ไปเรื่อยๆนะครับไปเรื่อยๆนะครับจนไปถึงจุดที่สิ่งที่เราเรียนรู้มันเป็นสิ่งที่เราเรียนรู้เป็นครั้งแรกของโลกก็จะเกิดเป็นสูตรทาชิโย
โอเค
ครับ
นี่เล็ก1 นาทีค่ะ
โอเคก็หมดเวลาผมได้จิบกาแฟพอดีนะครับเป็นยังไงตอนนี้คุณไปเจอว่าผมลืมใส่เลข7เข้าไปในไฟล์ Excel เนี่ยคุณรู้สึกฮึกเหิมไหม
ก็รู้สึกว่าว้าวตอนแรกว้าวไม่ตรงแล้วก็ค่อยๆมาไล่ดูค่ะว่าหนูทำไมทำไม่ตรงอาจารย์ลืม7
ความรู้สึกลักษณะแบบนี้นะครับที่แบบว่าคุณมานั่งแกะด้วยตนเองนั่งอยู่กับตัวเองนั่งตอบคำถามของตัวเองแล้วก็ไปเจอว้าวอย่างเงี้ยคุณต้องระวังให้ดีนะครับเพราะมันเป็นสิ่งที่มันเสพติดได้ง่ายๆนะครับมันเสพติดง่ายเรื่องของอาการว้าวเนี่ยเพราะว่าถ้าว้าวปั๊บแล้วมันรักษาไม่หายมันอยากจะว้าวไปต่อไปเรื่อยๆนะครับ
แต่ไม่ชอบความรู้สึกคิดวนนะคะอาจารย์แบบว่าแบบมันเหมือนแบบพอเราไม่ได้อะแล้วเราหงุดหงิดนะคะแบบไม่ได้เพราะอะไรวะติดอะไรเงี้ย
ผมก็หาอะไรทำอย่างอื่นพอให้กับค่าเวลาเล่นเกมออนไลน์หาอะไรกินสั่งแกร็บอะไรดูหนังดูทีวีนะครับ
ให้ลืมแล้วก็มาคิดใหม่เหรอคะ
ใช่ครับปกติผมจะไม่ลืมหรอกผมเก็บไอ้การคำนวณใส่ไว้เข้าไปในจิตใต้สำนึกอยู่นะครับ โอเค
เวลาเราดู
ตอนนี้
เราก็ไปคิดด้วยอ๋อหรือเวลา
ได้เวลาเดี๋ยว so I just got back from a coffee break with having a lovely discussion with my students. So I'm going to show you how you solve diffusion equation in one dimension. So what do we need? Let's look at the physics first. What I'm showing here is the animation I got from Wikipedia. There's a diffusion of gas molecules. In the beginning, you only put the gas on the left partition of the container, and then you take away the partition, then the gas diffuses from the left to the right. And at the end game of this process is that the whole container has the same concentration of this gas molecule. Okay, so but how do we do this calculation using computer programs and numerical method? So I begin by drawing my graph. This is my x-axis, and that is my vertical axis, which is the F. F is the concentration of the gas molecule. Now, because we have two variables, we have x and t, and therefore my function or my solution is a function of x and t also. See? So let's see. To solve an equation, you need to know what is called initial condition, the situation in the beginning at time t0. It's just like in this animation, you see that in the beginning, you have this on the left partition, and on the right, you have nothing in the beginning. And therefore, this is my initial condition curve. On the left partition, you have this full value of concentration. On the right, you have 0. Okay, that is my partition here. That is my time 0. Okay. So what do we do next? We then make my axis here into bunch of points, a set of points, x0, x1, x2, and so forth, and then we are going to use that calculation only on these points and not the entire line of function, but only on this point here. Okay, not in between, not there, but only at the point x0, 1, 2, 3, 4, 5, and so on. Okay, and so with that points, I then have to label my solution maybe this way. I say fi. I here tells you the position of the x value, like this here. If I0 is that point. If I2, it is that point over here. But also the f is a function of the time. So I need to have some way of saying the time here in my symbol. So I put this superscript t here to show you the time of the solution. Okay. So I begin to rewrite my calculus. This is in calculus form into my finite difference form. On the left-hand side, I have Laplace of the f. That's what we get. Very good. Now this Laplace here is only derivative respect to the x-axis, not the time. And therefore, the time value for my function on the left is always now, and now, at the moment, the time at the moment. But the point, the position here, we have this, my home in the middle, and these are my neighbor. The one on the right, the one here and here is my neighbor, divided by h squared. What about on the right-hand side of the equation? I have equal sign there. I have d constant, and here I have the derivative of the f, respect to time. So what do? I can go back to my forward difference. If I can go back, let me pause my let me pause my PowerPoint here. You know, just like any movie, any good movie, always go back to the beginning, like the Matrix movie. You know, you always go back to the beginning battle of the game. The same thing here with my lecture and how I design my lecture. If I go back to my beginning of the difference, there you go. Here's my finite difference, a forward difference. The point in the future minus the now divided by delta of the variable over there. So that's the forward difference for time derivative. Okay, there you go. I seem to have lost track of the series. Very good. So how we have here the f in the next step in the future minus f of the now divided by delta t. Okay, so I have that simple equation. I can then rearrange the term. How do I do that? I can move this d constant to the other side. Move this away. Delta t, move that away. So I get that expression over here. You see that delta t there and h squared d. So I have this expression. Now, what is so special about this expression? It's the same expression as on the top. It's the same equation, but one here has some special properties. Notice that on the right-hand side, I only have the f of the now, and now. What about on the left as the next? So this gives me an updating equation. If I have the information for the now, I can use this to compute the next time step. Now, you know, of course I know the d value, that's from the experiment, but I can also choose my delta t. I can choose my h, the spacing of the point of the x-axis. I can choose that, but I can choose that wisely. I can choose it to be something I want. For example, I choose the delta t and h squared such that this whole thing is 1/4, 1 divided by 4. That's possible. Or you may choose some other value, but I like this value because it's my lucky number. So I choose that value, and I put that 1/4 back to the expression. Okay, now what do I get? I get this final form of the updating equation, that the concentration in the next time step is equal to 1/4 of the neighbor. This is my neighbor. That's my neighbor, and 1/2 of myself, of the now time step. And that's the simple updating equation. Now let's do programming. So what should we do? What language should we use? For Dichen, it's C language because that's what she knows best. For Padrada's MATLAB, and I guess for Charida parts as either Python or R. But I am a professional, and as such, I will use Excel. Okay, I'm going to use Excel to show how to solve this problem, to do this programming, because professionals tend to use very simple tools to do difficult tasks. Okay, that's what we always do as an exercise. But it's going to be a very difficult exercise. So to prevent me from making mistake, I need to warm up a little bit. Okay, maybe give me half minute to warm before I begin to exercise my mathematic kung fu to solve this equation in Excel. I always do this really. I always exercise in the morning. I wake up 4 o'clock in the morning and I do my push up and all the things before I do my mathematics. Okay. So let's implement these problems in Excel. All right. So this is my Excel, and I can, let's see, to make it easier to see, I can zoom in. Okay. Now I can put this is my node, my node. Okay, node. And I can label. I can label my node. Let's say node number 0, number 1, 2, and 3, 4, 5, 6, 7, 8, 9, and 10. Okay, I don't forgot number 7 here. So with that labeling of the node, I can put this in column the x positions of the x position of the point. Let's see if I choose my edge, the spacing of the grid point to be 0.1. Therefore, my x going to be 0.1. That is my edge times the node label A3. If I copy these formula to other cells in Excel, I get that over here. But that is not really nice. Let me show the number in a very fixed decimal value. There you go. Now I have my x position. And next, I need to know the initial initial values. Let's say that's my. Let me change the label down there to make it here. This is my initial condition. Like I said, we need to have the information of what happens in the beginning of the simulation. The time here is time t0. Time t0. Okay. So what would be my initial condition? I would go back to the slide. So there, it's flat with some number and drop down to 0. Okay, so I go here back to my Excel. Let's make that 1, 1, 1, 1, 1, 1, 1, 1, and around here is 0, 0, 0, 0. So that is my initial condition at the time t0. Okay, let me maybe I can make this colorful a little bit here. There you go, my time. What about the next time step? Yes, my next time step. Well, depending on my choice of delta t, but let me just make it some number, and this is my next time step. It's C2 plus 1 over there. Okay, the time is as one time step. So I can then put my formula in this cell to update the value of the solution. Let me go back to the slide, see what the updating formula is. It's 1/4 of the neighbor. 1/4 there on the left and the right. And for myself, for my home, is 1/2. Okay, so let's go back to, let's put this formula here. It's equal to, okay, 1/4 of the neighbor. What is my neighbor? My neighbor is C3 there. C3, the blue color divided by 4, plus the next neighbor is C5 there, the red, divided by 4, plus the last one is my home. My home is C number 4. That's my row number divided by 2. That's what I have now. That's my the next value of the f. I can copy there and paste all the rest here to this cell. There you go. And also the number does not look very nice. I need to change the format of the number to show the same decimal place. Wait, okay. But I still have this here. The point on the leftmost, this point there, and the point on the rightmost, what do we do with that? Because this point has no neighbor. That point there, there's no neighbor on the right. What about this point there? It has no neighbor on the left. So what do we do with this boundary of the region? Okay, let's get back to the drawing board. What do we do with the boundary? Okay, so just like any solving differential equation, you would need an equation, you need initial condition, and you also need what is called the boundary condition. What happens at the boundary? Okay, that's what we need. So let's analyze the boundary condition. Look at what happens here on the left of the entire system. On the left here, okay. Now that's the gas molecules. The gas molecules, it move back and forth, but it hit the wall and always bounce back because there's brick wall here on the left. So hit the wall, always bounce back. Now how do we translate that into an equation? If the gas molecules as it diffuse hit the wall on the left, it always bounces back. It can never goes into the other side because we have this solid wall there. How do we turn this picture, this mechanism, this phenomenon into an equation? What would be the mathematical condition that happens on the left of this region? You can look at the graph there. Okay, it's always there. Any idea how do we implement the boundary condition for this specific example? แก๊สเลือกอนุภาคแก๊สมันเวลามันวิ่งมันก็ต้องสะท้อนกลับเสมอเป็นแบบนี้นะครับเพราะฉะนั้นเราสามารถจะเปลี่ยนไอ้ภาพนี้ให้กลายเป็นสมการทางคณิตศาสตร์ยังไงจึงจะสามารถที่จะเอาไปแก้คณิตศาสตร์ต่อได้นะครับแต่คุณต้องมีทักษะในการมองโลกใน2มุมมองเสียก่อนคุณต้องสามารถมองโลกในแง่ของคอนเซปต์ในแง่ของความเป็นไปของเรื่องราวของสตอรี่แล้วก็เปลี่ยนให้กลายเป็นความแม่นยำของภาษาทางคณิตศาสตร์อันนี้ก็ไม่ต่างจากนักประพันธ์ดนตรีนะครับคุณต้องรู้จักมีอารมณ์ศิลปินมีทำนองแล้วก็ต้องสามารถเปลี่ยนให้กลายเป็นบันไดของโน้ตกุญแจซอนมี5เส้นมีโดเลมีฟาซอนละเป็นระบบได้นะครับต้องเปลี่ยนกลับไปกลับมาได้นะครับนักฟิสิกส์ก็เช่นเดียวกันมีไหมเอ่ยไอเดียที่ว่าที่มันเกิดขึ้นในช่วงที่มันขอบของภาชนะเนี่ยทั้งซ้ายทั้งขวาเนี่ยความหนาแน่นมันต้องเป็นยังไงหรือมันต้องเป็นไปตามสมการอะไรเฉพาะจุดด้านซ้ายมือจึงจะสอดคล้องกับคอนเซปต์ที่ว่าแก๊สโมเลกุลมันพอมันชนปั้งมันต้องกลับคืนมานี่ไม่เอ่ยมันต้องมีสักคนคิดได้อะนักเรียนมาจากทั่วโลกถ้าเกิดว่าคุณเป็นตัวแทน
How about like a concentration is equal to 0 at both points?
Concentration is okay. Close. So one idea is that to force the F to be 0 at the boundary. Okay, but that violates the initial condition here. You'll see this initial condition there. It's not 0. It's some number, but something else is 0.
So basically on the right hand side is 0 and then on the left hand side is 1.
Right. The value itself is not 0, like on the left hand side, but something else is 0. What is that?
The rate of change.
Very good. The slope respect to the x axis. The slope is always 0. That's what it means. That's what the math for when a particle goes to hit the left wall, it always bounces back. In mathematic expression, the BC for that is the derivative of the f respect to the x. The x is always 0 at this point. The value can be something else, but the slope is always 0 over there. The same condition can be applied to the right boundary of the system. The slope of the f respect to the x must also be 0. Okay, so if we have that condition that the slope is always 0 on the left boundary and on the right boundary, how do we turn that into an Excel formula? ถ้าเกิดว่าเรามีเงื่อนไขที่ว่า slope ของเฉพาะจุดขอบด้านซ้ายสุดต้องเป็น0กับขวาเป็น0เนี่ยมันจะแปลว่ายังไงในมุมมองของการมาเขียนเป็นโปรแกรมนะครับถ้า slope เป็น0แปลว่าไม่มีการเปลี่ยนแปลงคือการเปลี่ยนแปลงเป็น0ลืมพูดเป็นภาษาอังกฤษ if the slope is 0 it means there is no change of the f value at least at the boundary. If there is no change, when you get back for this here, what is the value for this? It should be equal to C4. There you go. I am forcing this point of the time step to be the same as the one immediately next to it, C4. That's what I mean by having 0 derivative with the x direction. What about here? It's equal to that point immediately adjacent to this point is C12 right there. So we have the full formula for every point in the updating. Let me change just to make it look nice. The decimal point. There you go. There you go. That's only the 0. That's the 0 time. So how do we go to the next step? I just copy this and copy and then paste it to the next cell. That's the next time step, next time step, next time step, next time step. Remember the yellow painted cells here tells you the time. Okay, now next time step, next time step, and next time step. So we are having so many junk on the display. So let me hide this, and there you go. So we skip ahead from 0 to 10. Okay. And then again, I add next time step, 13, 14, 15, 16, and then to 20. And then I begin to hide this here. There it goes. It looks much, okay, it's canceled. There you go. Now it looks much better. Let's try one more. Okay, the last one. I paste that into the next, no, I forgot. I need to recopy these things here, copy, and then paste next time step 23, 24, 25, 26, 7, and then 9, and then 30. Very good. So now I can hide this and then plot the graph to see what happens. Okay. Oh, very nice. So let's do that. I select in the beginning this region of the Excel and I insert the graph. Let's see which graph I want. I want a scatter plot. Am I doing something wrong? Why don't I see the plot? Okay, that's X positions, and the that's strange. Maybe there you go. If I select only this, oh, okay, I'm getting there. Now I have this graph, for the initial time. It looks okay, just like what we wanted. If I go back to this initial drawing board, you get the same thing we want there. Notice that if you count the number of pigments, how many do we have? We have 1, 2, 3, 4, 5, 6, 7. You have 7 pigments total of the entire container. Okay, 7 pigment. 1, 2, 3, 4, 5, 6, 7. Okay. Now let's plot the graph for the next time step. Step number 10. Okay. So what do? We go there and then insert the graph. How do I insert the graph? Okay. Okay, there. I select data, and then I click add, and then I click series name. Let's say this is my series name, number 10. And what's my X value? Those are the X value. And what will be my vertical value? Is there? Yeah. And then there you go. Looks very good. You know, in the next step number 10, it diffuses. So it get to more of an equilibrium state. Let's go to the next graph. Let's see, I have here, I add more data, click add, and then select the name. Let's say number 20, and then I choose the X range as before. I click OK, and then I choose at the end the value of the there. Here you go. It gets closer and closer to the equilibrium. Okay. Now, suppose I have that Excel, and I change my initial condition. Instead of having all the color in the beginning on the left, I do this. I put all the color in the middle. Put everything in the middle, and we'll see what happens to the simulation. This was 0, 0, 0, 0, and 0, and 0, and this one is 7. There you go. That's what we get, okay? So the blue is the initial condition. As time goes on, the whole thing sprayed out, and fill the container at the end, like that. Okay, same thing. All right. Let's see. So that will be what we have. You know, the exercise of Excel and how we deal with solving diffusion equation in Excel. Now, if you use a much more advanced tools like Python or MATLAB or C, you will get much more advanced system, maybe in 3D, maybe in 2D, and so forth. But at least for the concept, that's all there is. Let's get back to the drawing board here. We have equation like so, and I begin to digitize or discretize the system into points, and then label the points, and I convert the equation from calculus form into finite difference form. Then I rearrange my terms so that it looks like the now always on the right hand side and the next is on the left hand side. I can then use that equation to update the solution from one step to the next, to the next, to the next, and so forth. Okay, so that's the end of the exercise for differentiation. Okay, let's go back to the beginning of this movie, this long journey of almost 4 hours of lecture time, integration and differentiation. And I hope that so far in this 4 hours, you have changed the way you see mathematics, that not only focus on the recipes, but also the ideas of how you do things, the ideas of how you compute the area below the curve, of how you look at the pattern, and how you interpret all these Laplacian and diffusion equations and so forth. Okay, so that's the last slide for today. We don't have homework this week because you already have a lot of homework problems, and I want to spend time grading your homework solution. So any other any comment that you want to add or question you want me to go back and resub in Thai in one of the aspect of the of the lecture. อย่างนี้
ครับอาจารย์ผมมีคำถามครับ
ครับผม
คือไอ้ตรง boundary condition นะครับเป็น
ครับ
มันเป็นdiff เทียบ x เท่ากับ0ใช่ไหมฮะแต่ว่าทำไมใน Excel อาจารย์ถึงดึงค่าของเวลาอีกไอเวลาก่อนหน้าไปแทนถือทำไมถึงไม่ใช้แบบว่าneighbor ในเวลาคอลัมน์เดียวกันนะครับ
น่าจะใช้ได้นะน่าจะใช้ได้มันก็จะต่างมันก็จะต่างกันในรายละเอียดนิดหน่อยนะครับลองดูนะครับ so the question is that when I say that the slope is 0 for the boundary condition, why do I use the value of the previous time step as opposed to of the current or the next time step? If I unhide all of these, okay, and then I change the formula. Now that's not going to be easy. You see, because that, let's see, this is my, here is my D4. I can set C D3 is equal to D4 to make it the same. Do that, I guess. And if I do that here, I can also do the same thing here. Must be equal to D9 over there. Okay. Am I missing something weird? Oh, D12. Okay, I'm sorry. D12. There you go, D12. So I'm doing D12, and that is D4. Okay. With that, I can simply just reapply that formula, copy, and then paste, and paste, and then keep pasting the thing. But now I've lost a track of where I've gone so far. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and so on. And we'll get to 30, and then we'll see the graph as our reward. There you go. Almost the same, but it will change a little bit because of the way you implement it slightly. Okay, but not conceptually different. Okay, let me get the same initial condition. 1, 2, 3, 4, 5, 6, 7. Okay, 1, 2, 3, 4, 5, 6, 7. Very good. Very good questions. How do we implement the? There you go. See. Same. All right, but it'll be different, at least in a very tiny significant figure. Okay. Very good. So the questions tells me that you have been paying a lot close attention to the lecture, and I'm very happy. I forgot. I'm very sorry. I forgot. Who was that? Was that Dewey or Tosapun? Okay, very good. Just your TT name is like the crying emoji. Okay. Very good. So let's ask Dishen. So are you happy because you're the one who made the request for the diffusion? So are you happy with the material today?
Yes, Ajahn.
Very
I
good.
Understood fully.
What?
I understood clearly.
Totally. So that will be the lesson for you guys. So if you guys want to know more about the things that you want to know, just tell me. Give me a request so I can go and prepare my lecture to fit your happiness. Okay. All right. By the way, if you know, I have not put that in my PowerPoint, but if you know you now the question is, if you don't care about diffusion, you know, like you are interested in some other topics สมมติว่าคุณไม่ได้สนใจใยดีมากมายกับสมการการแพร่แต่คุณไปชอบเรื่องอื่นแล้วคุณจะมีโอกาสได้ไปพบปะเจอไอ้สมการนี้อีกไหมนะครับ but you will see this equation all the time in physics. For example, you may notice that the Schrödinger equation is a diffusion equation. Okay, I have not put that in my slide, but let me do this quickly here. If you go to Wikipedia and type in Schrödinger equation and look at the form of the Schrödinger equation in Wikipedia, okay, you see that that's the not. You have this simple. Very good. That's the form there. You see there that on one side you have this d dt. That's the same thing with equation of diffusion. On the other side, you have second order derivative respect to the x. Do we have that? There you go. Okay, there you go. So this quantum mechanics equation really is a diffusion equation with complex number constant. Okay, because back here we have a d as a real number, but for quantum mechanics, the d here is an imaginary number. So you always need to see this equation anyway in quantum mechanics. What about if you don't care about quantum mechanics? You don't care about การแพร่ but you care about heat and the equation of heat. It turns out that the equation of what we call the heat equation is also diffusion equation. Okay, heat equation. Okay, let's say, do we have there? Okay, that's the heat equation. I need to give you a better there, but basically that is the heat equation there. Okay, this one tells you the temperature of at any point on an object. On one side, you have this Laplace operator, and the other side you have this d dt. Okay, first order derivative of the time. So that is also diffusion equation. But T here is the temperature of any point in the system. So you always have to in your life encounter diffusion equation all the time, one way or another. And I hope that this lecture is going to be very useful for you to interpret and understand the meaning of all the math involved in the diffusion equation. Okay, so with that, let's wrap up the end of the lecture. So Di Chen has made this request in diffusion, and she said she's very happy about that. So let me then ask just quickly for all of you to just give me a keyword of your request, okay, on the top of your head. What would be your request? Nothing serious, just give me something to work with. What about you, Padrada? What do you want to see? Just give me a topic that you would love to see. So if I'm happy, I can put that in my next lectures.
I need to see about nuclear.
The nuclear physics, the equation of in fact, in nuclear physics, we have this magic number. That's a very good story. A story of a magic number in nuclear physics. So what about you, Chanidapa, Kun Panda? What will be your keyword that you'll be very happy to see in our lecture?
I don't know for now because of I'm happy that you talk about diffusion because I use it I have to use it in drug talking to see
Okay.
the drug. Yeah. For other, I don't have it now, but if I have it, I will tell you. the
Very
next
good.
week.
So maybe you want to know more about diffusion in more detail. Okay, because I
Yeah.
have not talked about other term. In diffusion, you have more term than that. In diffusion, you have that term and that term, but you also have another additional term. Like for example, in Schrodinger equation, you have that term, second derivative of x, first of t, and also additional term here. What does that mean? How do we interpret that term? Or in the heat equation, you have the second order of x, y, and z, the first order of the t, that's okay, and another term over here, okay? What does that mean? Okay, the meaning of this in the diffusion equation, okay? What about the other two gentlemen from faraway land? What would be the topic on top of your head that you can give me and that you will be very happy to to hear? Dewey, 1994.
Actually, I don't have much like idea now. But how about like because of you already talked about the diffusion equation, right? How about like Navier-Stokes equation?
Navier-Stokes equation, much more advanced, but I guess I can manage to make it simple and short enough to compress it within half or an hour. Very good. Okay, I'll do that. Interesting. What about the Totsapon? What would be a topic or any keyword that you are interested in?
อืมตอนตอนนี้ผมสนใจแบบว่าควอนตัมเมคานิกส์ครับแต่ว่าอาจจะดีถ้าแบบว่าได้เข้าใจแบบว่าพวกกรุ๊ปเวโลซิตี้อะไรเงี้ยฮะที่แบบว่าเขาใช้ฟูเรียร์ทรานส์ฟอร์มอะไรเงี้ยครับเพราะว่าผมยังไม่มีความรู้แบบว่าคณิตศาสตร์ตรงนั้นมากเท่าไหร่ครับ
Okay, so you want to know more about momentum space of quantum mechanics, of how you see things, not in terms of positions of where the particle is, but in terms of how fast the particle is moving, or the momentum of a particle. Very good. Okay, so I'll go do my things and work my magic, and I hope you will be happy in the future. So before I leave today, any comments that you want to make, or any question that you want to ask, maybe about your score, anything. Let's put soft music just to make the room and the environment much more relaxing. You know, you can sit there and breathe in and breathe out. And imagine you're in your room, it's very peaceful and far away. Oh man, I love to talk in English. My English is good because I had a chance to teach in English when I was in US, and that was a superb experience for me. Yeah. Okay. All right. All right. If there is no any other questions, I will see you next time. Thank you for being with me and be my company for all these 2 hours. I'll see you later.
Thank you so much, Ajahn.
สวัสดีครับ